Hey, welcome back, class. We enter our final exam review week. I know next week will be our final exam, so I'm going to start off with today just a couple of chapter summary reviews, just some brief questions from each chapter just to hit on some of the topics, refresh your memory. So the first worksheet we have is like a chapter 1 to 3 summary. That's like linear functions and rate of change, domain and range, a little bit with quadratics. Those were all chapters 1 to 3. Optimization was also thrown in there with limits when we did domain and range, but we'll do those under a separate review sheet later on in the week. All right, so let's see as we get going here. So a couple basics, find f of 1. Here's a graph. Just make sure you know how to identify at x equals 1. There's that spot. So f of 1 is equal to 1. So that's an easy one. And then where does the function equal 0? That's a y value. So this is an x value input. There's a y value output. So y equals 0 is right here. It's going to hit in two spots. So those two values are going to be 0 and 2. Just be mindful that there are two times that it does happen. Okay, f of 0 is 0 and f of 2 is 0. Next one is a linear functions modeling application question. So probably an appropriate situation from most of you coming up soon within the year. I know my daughter's going to be encountering this with meal plans and decisions like that coming up soon. College meal plan, you have a membership fee. All the meals you get are a fixed cost. So if you buy 5 meals, it's this. And if you buy 10 meals, it's that. Essentially what that's doing is giving you an X and a Y coordinate. 5 meals, the output is $122.50. And if you buy 10 meals, the output is $145. So we're going to use, you could use a linear regression, but if it asks you to solve algebraically for this, the first thing you'd have to do is find the slope. So 145 minus 122.50 divided by 10 minus 5. That's just delta y over delta x, y2 minus y1 over x2 minus x1. So this comes out to be 4.5. So that slope value is the price for each meal. So that's the per meal cost. We still need to know what that membership fee is. That's like that fixed fee, which is the equivalent of the y-intercept. So you can go back to y equals mx plus b, and we can go back and substitute 4.5 into here. So y is equal to 4.5x plus b. Then you can substitute any of those values for x and y. So 145 equals 4.5 times x and then plus b. And when you solve for b in that case, that b value is going to come out to be $100. So you have a meal cost. The meal, that cost is $4.50 per meal. It's the cost. And the membership fee is going to be a flat cost of $100. So when you sign up, it's $100, and then each meal beyond that is $4.50. So find the cost of 35 meals. Well, we have a function now for the cost, f of x. It's going to be 4.5x plus 100. So 35 meals would go there. This is just going to be 4.5 times 35 plus 100. So that value would come out to be about $257.50. So there's your total cost for 35 meals. On the flip side of that, this one is now a y value. How many meals would you be able to get if you had $300 set aside for your meal plan? So your y value is going to be 300, and we're going to find out what x that becomes. So if we minus the 100 over, we get 200 is equal to 4.5x. And then when we divide by 4.5, you'll get that value of x. That comes out to be 44.44 repeating. So you can get 44 meals. You can't get the 45th meal. So therefore, you would have 44 meals. All right, moving on to domain and range questions. All right, so that's at the bottom of the page here. So a couple things you could do if you remember a little bit about domain and range. One thing is if you remember about radicals, the radicand always has to be bigger than or equal to 0, but because it's in a denominator, we can't have it equal 0. So in this case, x would have to be bigger than 3 when you have the 3 over. So that's the algebraic way to get the domain. You could also graph this, and you'll see when you graph this out, you'll have an asymptote, and the graph will look something like this. It's going to go down towards the x-axis. So y is going to approach 0 as x goes out to positive infinity. So because of this, you could kind of tell, oh, sure, x is greater than 3, because here's positive 3, and it's everything above the x-axis. So in this case, we would have y is greater than 0 and x is greater than 3. All right, moving on to page 2 of this worksheet. So let's get this set back up. Some oldies but goodies. Here's a little bit with quadratics, if you remember, and rates of change and difference quotients. So evaluating f of -3, well, that's pretty simple. Let's just plug -3 in for the value. Or you could type this into y1 and go to the table of values. So this would be 3 times -3 squared plus 4 times -3, and then minus 10. So that's going to come out to be a grand total of 5. Not too hard. That's pretty easy. Difference quotients. All right, f of x plus h. So let's do the f of x plus h part right here. That means you're going to plug x plus h in where the x's are up there. So where you see an x plus h, or rather where you see an x, you're going to replace it with x plus h. So what that turns out to be is 3 times x plus h squared instead of x squared, plus 4 times x plus h, and then minus 10. So that's your f of x. So if we highlight that, that's this. Okay, now what we're going to do is we're going to subtract all of our f of x functions. So we have to put the entire function. That's going to be all of that. So when we put that in here, it's the green stuff, that's 3x squared plus 4x minus 10. And all of that is going to be divided by h. So we got to do a little double distribution here. This is x squared plus 2xh plus h squared. That's that distributed. And then this is plus 4x plus 4h. That's that. This is going to be distributed all the way through. So it's going to be minus 3x squared minus 4x and plus 10. So if we write that out and we distribute the 3 here, 3x squared plus 6xh plus 3h squared, that's distributing the 3 to here. And then we have plus 4x plus 4h minus 10. That takes care of all the orange stuff. Okay, so again, if we highlight that, all of that is the orange. And then on the green, we have minus 3x squared minus 4x and plus a 10. So all of this is all of the green stuff. And again, we have that all over h. So remember, we're going to get terms to cancel out, right? So here's a positive 10, here's a negative 10. Here's a negative 4x, there's a positive 4x, and here's a negative 3x squared, and there's a positive 3x squared. So every one of the function terms should cancel out. What that turns out to be is 6xh plus 3h squared plus 4h, and all of that is all over h. So if we cancel the h's here, here, and here, and we cancel out that h, we're left with 6x plus 3h plus 4. So 6x plus 3h plus 4 represents the average rate of change for some interval size h. If we take the limit as h approaches 0, that term drops out, and you're left with 6x plus 4. And if you go back to the original function, there's the original function. If you remember, you can find the derivative, which would be where the h approaches 0 and drops out. 6x plus 4 comes from 2 times 3 is 6, and then it's x to the 1 less, so 6x to the first, plus 4, the coefficient of the x. So if you remember a little bit about from earlier when we were talking about derivatives. All right, the bottom questions, a couple composition questions. We've got 3 different functions, f, g, and h, and these are compositions. So the first one says we're going to take g of x and we're going to plug it into the h. So here's our g of x function, and we're going to plug it in where the x is. So what that one looks like is 2 over 1 minus, and then this is where we are going to put that g of x function. So g of x happens to be x squared minus 2x. So we could distribute the negative, and we get 2 over 1 minus x squared plus 2x. And if you just write it in maybe a standard form, 2 over negative x squared plus 2x plus 1. There's kind of the expression that you would have. All right, going further to the bottom one, here's the inverse, if you remember. So we're going to find the inverse of f. So here's our function f. So if y is equal to 2x minus 5, for the inverse, we're going to switch the x and the y. And so now we just get the y by itself. So x plus 5 is equal to 2y. We can divide by 2. and we get our new function x plus 5 over 2. And so if it's x plus 5 over 2, we would write then f inverse of x is equal to x plus 5 over 2. And there's a few ways you could write that. That's also like 1/2 x plus 5 halves, and other ways you could write that as well. All right, that's it for chapters 1 to 3. Let's move on to chapters 4 and 5, which are exponentials and logs. So a quick review of some of those. All right, so top of this worksheet says, do you know how to write the equation of an exponential function given some coordinates? Now, of course, here's your x and y, so it's basically like you've got -3 comma 54 and 2 comma 2/9. You could always do an exponential regression just to check your answer to make sure it matches what you get algebraically. But if you recall, we were doing y equals ab to the x, and do the same thing over here, y equals ab to the x. And if you divide these out, you're going to get the a's to cancel. 54 divided by 2/9 comes out to be 243. That's equal to b to the -50. Subtract the exponents. -3 minus 2 is -5. And then when we want to get rid of that exponent, we can raise both sides to the reciprocal exponent, and that cancels it out. So this is going to cancel out, and we are left with b is equal to 1/3. It's a rational number. So that worked out pretty good. Now we can use that to substitute back in. So y equals a times 1/3 to the x, and we can take any coordinate and plug this back in. I'm going to use the integer value ones. 54 equals a times 1/3 to the -3. That comes out to be 54 equals a times, this is 27. And if you divide by 27, you get a turns out to be 2. So because of that, we now have our final equation, y equals a, that's 2 times b to the x. 2 times 1/3 to the x. All right. Moving forward, we've got compound interest questions. So these are all 3 questions that are going to kind of be related to the initial setup. So let's just zoom in and carefully look on that. So if you remember 4.5% interest compounded quarterly, you might recall 1 plus r over n to the nt. So the a value is the initial, the r is the percent rate as a decimal. So this would be point right here, 0.045. Compounded quarterly means the n value is going to be 4 times a year. So when we write that out, what's the effective annual yield? The effective annual yield is essentially what that value is right there. It's like the b value, a, b to the x. It just happens to be that the b value is spread out multiple times throughout the year and divided up. So all we need to do is evaluate that orange box. So when we write that out, it's 1 plus 0.045 over 4 to the 4, right? So this is approximately, and it's going to be an ongoing decimal, but 0.045 765. And there's some more decimals after that. So if you notice, this is like 4.5765% approximately. So 4.5765%. That's about the percentage that you would have every year, because you're taking 4.5% and you're breaking it up and dividing it up 4 times throughout the year. So you get a little bit more than 4.5%. All right, so now we take a look at the next question. I want to open an account with an initial deposit of $2,000. How long will it take? It's the nearest 10th of a year for your account to reach 5,000. So 5,000 is going to equal 2,000, my initial investment, times 1 plus 0.045 over 4 raised to the 4t, and we're looking for the t. So one option you could definitely do is you could put this into y1 and you could put this into y2, and you could graphically find the intersection. Okay, that method would look something like here's 2,000 and raising up, here's 5,000, and you would find the intersection after a certain number of years, maybe, guessing somewhere around 15, 20, 25, 30 years. Okay, and you would open your window up in the x direction accordingly, find the intersection. If you're going to do it algebraically, probably the easiest thing to do is to reduce this base to its regular b value. So 1.045765 to the t. Now you've just got a constant, a singular base term, and the exponent. So the first step is to get rid of the coefficient. So we get rid of that. And we get 2.5 is equal to 1.045765 all to the t. And at this point, since it's just a simple exponential, we can put in a log on both sides. And then this t would go out in front. So we have now the log of 2.5 is equal to t times the log of 1.045765. Last step is to divide that over, and you have your t value. Comes out to be about 20 and a half years. Okay, rounded to nearest tenth. So the last question is a situational question. You have your bank account, and your bank account is growing, right? Same $2,000 initial deposit, and it's growing at that same rate. So 1 plus 0.045 divided by 4 to the 4t. So there's your account. And you want to find out when your friend's account, who opened his account or her account, this one says his. So this is 1750, and it incurs 5% annually. So that's just going to be 1 plus 0.045 to the t. So this is the situation that we're in. Again, you could put this into y1, and you could put all of this into y2, and you'll see one account starting at $2,000 growing at 4.5%, and then the other one starting at $1,750 but growing a little bit faster at 5%. So at some point they're going to intersect. So you could find that intersection. So that is definitely one way. And again, you'd open the window up 20, 30, 40 years to see where they intersect. The algebraic way is to set up and get the coefficients to the same side. So I'm going to divide the 1750 over, and I'm going to divide this number right here over to that. So we have 1.05 to the t divided by, and I'm going to use the one singular number for that base instead of all of it to the fourth. So this is going to be 1.045765 all to the t, and that's going to equal 2,000 divided by 1750. So now this can be rewritten as just one big base. This is 1.05 over 1.045765 all to the t, and that's equal to, again, that 2,000 over 1750 number. So now we've got the base by itself. We just put in a log on both sides. That t is going to come out in front, put a log in over there, and then we can divide this term back over. So what we get is t is equal to the log of 2,000 over 1750 divided by the log of 1.05 over 1.045765. And when you work that number out, it's about 33 point something years, but it rounds to about 33.0 to nearest tenth of a year. So there's your first page. All right, moving on to the second page. So, and last page for this worksheet. So a radioactive substance decays at 2.5% continuously. Find the half-life. So half-life questions, 0.5 equals b to the t, but this b value is a continuous decay rate, so it's actually going to be e to the negative 0.025 t. So there's your setup. The only thing we have to do now is use logs to solve, but because it's a base e, we're going to use a natural log. It's going to be simpler with cancellation. So what we get is the ln of 0.5 is equal to negative 0.025 t times the ln of e. And that's the reason why we like to use ln's, because the ln and the base e cancel each other out. So now all we have to do is divide by negative 0.025, and you'll have your number, t is equal to the ln of 0.5 over negative 0.025. And that's approximately 27.7 years. All right, then we go to number 4. This is just comparing the effective annual yields for each. So for that, all we got to do is set up those base values, right? So this, the 1 plus r over n to the n, that's the part that represents the effective annual yield. All right, so we're just looking for this part right here. What does that turn out to be? Because that's going to tell you what the rate of return is each year, and then you can rank them for which one is best. So for the first one, 4.9% compounded quarterly, it's going to turn out to be 1 plus 0.049 over 4 to the fourth. And you can find out the approximate decimal there. This is 4.85% monthly, so it's a lower percent rate, but it happens more often during the year. So 1 plus 0.048 divided by 12 to the 12th. And then what does that decimal come out to? Here's 4.8%, but it's every day divided up. So a smaller percentage, but yet happening more often again. So this is 1 plus 0.048. Oops, sorry. This one was 485 up top, 4.85%. This is 0.048 divided by 365 raised to the 365th. And what does that come out to be? So if you find out these decimals and you put them in order from highest to lowest, it actually turns out that A is the highest, B is the next highest, and C is the third highest. So the percentage rate really has a bigger impact than the amount of times you're dividing it up per year. Okay? All right, down to the bottom, go to logs. Remember that square roots are like exponents of a half, so those are like coefficients of a half. Products turn into addition, and fractions or division is a subtraction. So this is going to be the log of A, takes care of that one, plus 1/2 log B, that takes care of that one, and then minus the log of C. So when we get to all that, that happens to be choice 1. All right, and then down near the bottom, all the algebra, solving these algebraically. So, oops, sorry there. All right, so we're going to set these up. The first one just has an exponential on one side and a constant on the other. So when that's the case, get the constants together. E to the 3x equals some number, d over a. So at this point, because it's a base e, we would use the natural logs on both sides. And then again, this is just going to go out in front. So 3x times the ln of e is equal to the ln of d over a. That's some constant. And then that is just 1. So if we divide by 3 to both sides, we get x is equal to the ln of d over a, and then divided by 3. And whatever that constant term comes out to be, there's your final answer. In the next case, you've got an exponential equaling another exponential. Okay? And so we have this 2 plus x. So this is a little bit of an issue right here, that guy. So this is the same as d squared times d to the x. That's d to the 2 plus x. When you have the same base, you have the exponents. So I'm going to rewrite this expression, and I'm going to write it as m times n to the x is equal to c times d squared. Those are all constants, and then times d to the x. There's the exponential part. So now you're going to make a decision. You want to bring the constants to one side and the bases to the other side. I'm going to divide the d to the x over. So I'm going to get n over d to the x. That's dividing this term to that. And then I'm going to divide the m, which is the constant over here. So cd squared divided by m. So now you've got your exponential part on one side and your constant on the other side. We can take the log or the natural log, it doesn't matter which. And then this exponent is going to go out in front. So when we rewrite that, x times the log of n over d, and that's equal to the log of cd squared over m. All you have left to do now is divide by this constant right here. So we're going to divide by that, and we get our final answer, which says x equals the log of cd squared over m divided by the log of n over d. And here's your final answer in that case. Oops, sorry, went off the screen there a little bit. All right, hopefully that worked out well for you. We'll pick up with tomorrow during Tuesday's worksheet. We have chapter 7 and 9, which is trig. And then during the Zoom class, we'll be going over some limits and optimization problems. And then I'll have all of those answer keys posted Tuesday afternoon and Wednesday. All right, good luck, guys. Enjoy the week.